Okay, so this is going to be Calculus section 2.4. I am actually going to present 2.4 before 2.3 intentionally. This section delves into a concept called continuity. You've probably heard me mention continuity in previous videos. I've been sort of foreshadowing it. So I want to get continuity figured out before we get back to 2.3. So you are watching in the correct order. All right, so I've got this graph laid out here. This is a pretty wacky looking graph, but this one is going to highlight a bunch of different points that I want to make. So what we're going to do is we're going to take the graph. It is a function, by the way. This is the graph of a function. It seems to have some bizarre points, but it passes the vertical line test. So we're going to take this function and we're going to look at its value at different x coordinates, and then we're also going to look at the limit at those x coordinates. So let's start with 2. What is f of 2? We're going to say this is called f. Well, f of 2, if we look at 2 here, there appears to be an open circle. So in fact, f of 2 is undefined. I'm going to abbreviate that UNDEF, undefined. Okay, sure. What's the limit of the function as x approaches 2? That's a different question. What does the function appear to be approaching? We can answer this question graphically. Looking here, we can see this graph appears to be approaching this open point right here, which is at height 2. So despite the fact that the function is not defined at that point, it's clearly approaching 2 from both the left and right sides. So that limit is 2. Okay, let's look at what's going on at 4. What's f of 4? At 4, right up here, we see there's 2 points. One of them is open and one of them is closed. You can't have 2 closed points because then the function would be defined with 2 different output values for the same input. It would not be a function, in other words. But this is fine. The output value for x equals 4 is going to be determined by the closed circle here. So that would be when y is 3. So f of 4 in this case is 3. But the limit in this case doesn't exist. So I'm going to abbreviate doesn't exist as DNE, does not exist. So the reason for that is because the left and right limits would be different. The limit as x approaches 4 from the left is 4. You can tell the function is approaching this open circle, which is at height 4. But the limit from the right would be 3. So those are not the same, and so therefore this overall two-sided limit doesn't exist. Next, f of 6. Okay, there's no actual point plotted at 6, it's just part of the curve, but that's fine. There is a point there. You can put a point anywhere on the curve if you want to. So I can plot this with a dot, all right? That's there, despite the fact that it wasn't drawn there before. And so at 6, we can see the function is defined to give us 1. And the limit of the function as x approaches 6 is likewise 1, because it's approaching, not only is it not only is it defined at that height, it's also approaching that height. In other words, the dot is on the curve. Okay. All right, at 8, we have something interesting going on. At 8, we seem to have a vertical asymptote. Well, that is an undefined function there, and also an undefined, or a limit, which does not exist. So we have that. And then lastly, I want to look at 10. The function value at 10 is given by the dot, the closed-in dot, which is up here at, it appears to be about height 4. But the limit value at 10 is different. You've probably heard me say before that the limit doesn't care what the actual function value is. Not really. Often they coincide, because a lot of times we will end up evaluating a limit by evaluating the function, but it's only when it's continuous. Getting to that. In this situation, what the limit really cares about is what's going on near the value that x is approaching. So what's going on near 10, not at 10. We don't care what's happening at 10. And this example really highlights that, because we can see that at 10, the function value is 4. But that has no bearing on what the limit value is. The limit value is what the function is approaching as we get close to 10, and that is clearly 2. Right? Because this open circle here that the curve is getting close to from both sides, That's at height 2. So this example here basically demonstrates that the function value and the limit value are not associated with one another, right? Like they don't have to agree. There are examples where they're different. There are examples where they're the same, like at 6. There are examples where one exists and the other doesn't, and there are examples where neither exist. Okay, so there's no correlation between them. They are related to each other sometimes, but only when the function is continuous. So let's finally get together a definition of what we call continuity. So our definition of this: f of x is continuous at an x value c if 3 things. First, f of c is defined. Okay, we have to have an output, meaning c has to be in the domain of f. 2, the limit exists as x approaches c. And 3, they are equal to each other. The limit as x approaches c of f of x is actually equal to the function value f of c. And that is the defining feature and also the most valuable thing about continuity, at least for our purposes, is that the function value and the limit value at that number are the same. So let's see. So with that as our continuity definition, we can see that for the points that I examined over here, the only case in which it was continuous was this case at x equals 6, where the function value and the limit value were both equal to 1 right there. So that's a point, 6 right there is a point where it's continuous. But it's not the only point on this curve where it's continuous. Actually, anywhere where we see continuous curve, right, anywhere where you can draw the curve without lifting your pencil off the paper would be a bunch of points where the function is continuous. So this function I drew is continuous all the way along here, and then there is a point where it's not continuous, and then it continues up. It's continuous along there, it's continuous along here, and at 6 and blowing right through 6, and then going up here, it's continuous all along this curve. There's a discontinuity where it sort of jumps. It's continuous along this curve and continuous along this curve. So there's infinitely many points where it's continuous. We have these discontinuities. Discontinuities are points where the function is not continuous. So we can see in our graph here that, not that one, but I guess this thing, and this point here. These are 1, 2, 3, 4 different places where the function is discontinuous. And we have different types. One type of discontinuity is called removable. Removable means that you could just redefine the function at that x coordinate to make it continuous. So they usually look like this. Right? That's an example of a removable discontinuity where the graph is coming along and then there's a little hole and then it keeps going. We've seen these before. This is removable. I'm going to abbreviate that, remov. That one's removable. We could define the function there. Currently it's not defined, but we could define it to equal 2, and then it would become continuous. Similarly, actually this one's removable as well. The other thing is, rather than define, you could redefine the function. So at 10, the function output is 4, but we could redefine that to be 2, and then it would agree with the limit value and become continuous. So those are both called removable. The second type of discontinuity is a jump discontinuity. So that is, as you can imagine, a spot where the limit from the left and the limit from the right are different from one another. So that's the limit doesn't exist for that reason. So this is an example of a jump discontinuity. The function could be defined or not, either at one of the 2 limit points or somewhere else. It doesn't matter. It's still called a jump. And the third type is an infinite discontinuity, which is basically a vertical asymptote. Like, for example, something like that. We have one right here, inf. So that's the concept of continuity. this is the formal definition here, but you know, the basic idea is like it's a continuous curve. You could draw it with your pencil without lifting it off the paper. That's continuous, and we're going to use that concept as we go along here.